Welcome back, everyone. In this lecture, we're going to talk about the watershed algorithm. In geography, a watershed is a land area that channels rainfall and snow melt into creeks, streams, and rivers, and eventually even to outflow points like reservoirs, bays, and the ocean. These watersheds can then be segmented as topographical maps with boundaries. So again, watershed basically just telling you where the water ends up, and as you may imagine, the lower the land level is, the water will then drain into those watersheds, which you can then map as topography. And notice here that when this topography mapping happens, you get these segments. And metaphorically, the watershed algorithm transformation that works on images is going to treat the image it operates just like a topographical map, with the brightness of each point representing its height. And then it finds the lines that run along the tops of these so-called ridges, essentially trying to apply the same fundamental idea behind the way water aggregates in different topographies to the way brightness aggregates in images. Any grayscale image can be viewed as a topographic surface where high intensity denotes peaks and hills, while low intensity denotes valleys. The algorithm can then fill every isolated valley, or the local minimum, with different colored water, in this case, labels. So it'll actually be coloring the different segments of our image. As the water rises, essentially the intensity, depending on the peaks, those gradients nearby, the so-called water from different valleys, that is the different segments of the image, they're going to be filled with different colors. And if they end up meeting each other, you could imagine that those colors would start to merge. Just like if a lake was right next to the ocean and they were getting closer and closer, those two bodies of water would end up merging. So to avoid this merging, what the algorithm does is it creates a barrier. Essentially, it's going to segment edge boundaries in locations where the so-called water merges. Essentially, where pieces of different brightness levels end up merging, it's going to create a boundary. Now, this algorithm is especially useful for segmenting images into background and foreground in situations that are usually difficult for other algorithms. And a really common example of this is the use of coins next to each other on a table. So here we have an image of a bunch of coins right next to each other on a table. For a human looking at this image, it's really easy to see that you have separated coins on a table. However, for a lot of computer vision algorithms, they just see a dark blob on the background of white. So it may be unclear to the algorithm if it should be treated as one large object or many small objects. In fact, it may actually just grab everything in the foreground and treat that as one object versus the black background. The watershed algorithm can be really effective for these sorts of problems. In fact, it'll be able to detect, due to the way the algorithm works, the actual boundaries of these different segments. And then we can actually isolate and segment all these coins individually, as a human would. Later on, we're also going to learn how to provide our own custom so-called seeds that allow us to manually start where the valleys of the watersheds go. That way, we'll be able to then highlight, for instance, the sky on an image of a landscape, and then we'll be automatically able to fill in that as a particular segment. So for example, here we have an image, and we end up labeling our own seeds just by clicking. Notice how the colors are basically corresponding with each other. So the grass that's nearest to us, that's all a lime green. Then the rock on the right-hand side, that's all a purple. So these are setting seeds, and then you can apply the watershed algorithm to the specific seeds that you set manually, and it will automatically then segment the image as you seeded it. So notice now the grass has been automatically segmented from the other elements that were seeded with the same colors. Let's begin by exploring the syntax of the watershed algorithm with OpenCV, and then in the next couple of lectures, we'll expand this idea to setting our own seeds. I'm going to hop over to a Jupyter lab now. All right, here I am at a Jupyter notebook. I've gone ahead and done my imports as well as this display function that we've been working with. What I will do now is the following. I'm going to load up an image called SEP_coins or separated coins. And let's say CV2 image read, and inside of the data folder, there's an image called pennies.jpg. Let's go ahead and display those pennies. I'm going to hit enter here and say display the separated coins. And when we run that, I didn't actually provide a color mapping here. and it's just going to show the pennies. So we have these pennies, and notice how close they are to each other. For humans, it's really easy to tell that there's 6 separated pennies here. But as we previously mentioned, a lot of computer vision algorithms treat this as just a giant blob, and then everything else is a white background. So let's imagine that our task is to actually segment this image into 7 different segments, 6 for the coins and then 1 for the background. I'm going to show you, using techniques that we already know, what the result would be. The result actually doesn't work. It's going to segment this all as one image, but I want to show you the approach with what algorithms we know so far, so you can tell just how effective the Watershed algorithm is when we apply that one. So let's get started. The steps we're going to be taking is, first, we will apply a median blur to the image. The median blur will help us get rid of features that we don't really need, such as the faces on the coins themselves. And if you have a keen eye, you'll notice that one of these is actually a 2-cent euro. They're not all pennies, but we're going to try to blur the image. That way, we're really only focused on the circles of the coins themselves. Then what we're going to do is convert it to grayscale. And technically, the order of these two doesn't really matter too much. And once we have it in grayscale and we have it blurred, we're going to apply a binary threshold in order to make it black and white. And then that way, we can then find the contours. So we're already familiar with all 4 of these steps. We've had lectures on each of these individually during the image processing section of the course. So let's try applying this and see how it works at finding these actual coins. And we'll notice again that it doesn't actually do the job completely. So for the blurring, we're just going to say SEP blur for separated coins, blurred. I'm just going to choose a median blur and pass in separated coins. And remember, we just provide a kernel size here. I'm going to provide a pretty large kernel size because this is actually a really large image. Notice it's 4,000 by 3,000 pixels because I took this with my phone. My phone actually has quite a lot of megapixels on it. So we're just going to run that. And then let's go ahead and display the results of that blur. And there's the result of that blur. Okay, then the next step is to actually convert this into grayscale. So what we're going to do here is say gray separated coins is CV2, CVT color. I'm going to pass in the separated blurred coins and then go color. I think right now it's in BGR, and then we'll go to gray. And whoops, let's say CV2 color underscore BGR to gray. Let's actually display it now. Gray separated coins. And there we have it. So now we have gray scaled and they're a little blurred, so we don't have to worry too much about the facial features or the number 2 on that coin there. Now it's time to apply a binary threshold. So we separate it out into just foreground and background. Let's try this out. We'll say RET. And then separated coins threshold is equal to CV2 threshold. We're going to pass in that gray separated coins, and I'm just going to apply maybe 160 to 255. As we mentioned, you kind of mess around with that middle value as far as the threshold, but in our case, we are going to do a binary threshold. However, it's going to be inverted. That way, the foreground ends up being white. So run that and display the results. And here we have our results. And again, you can play around with this middle value. You can try something like 127 and see how that works. But you'll notice as you go a little lower, you end up getting distortion due to the faces on the coins themselves, which is why I pushed it up just to 160. And you're probably already noticing there isn't a nice way to go about this without your computer vision image processing algorithms attaching the coins somehow. There may be some erosion we could then do, but that would end up eroding from all the boundaries, not just these connections. So different approaches we could take here. I just want to show you just how difficult this task is given the image processing algorithms that we know right now. The final step is to actually find the contours. So we'll say image, contours, and then hierarchy. And we'll say CV2, find contours. And I'm actually going to make a copy of the threshold. That way I don't mess it up. And then we're going to use the methods that we used in the lecture, just these default methods, CV2, RTR underscore CC comp. You should be able to tab autocomplete these. And then we'll use chain approx simple. So now that we have that, we're going to just do what we did in the contours lecture. We'll say for I in range, the length of contours Whoops, make sure I actually spelled this right. Length of contours, lowercase, if the hierarchy at 0, I, 3, and if you don't remember this, go ahead and review the lecture on finding contours. If it's equal to -1, then we know it's an external contour. Right now, we're just looking for external contours, and hopefully there would be 6 of them, 1 for each circle. Now, we can see that's already unlikely given the fact that there seems to be connections in this binary threshold. So we're going to say -1, and then say CV2, draw contours, pass in the separated coins, the contours themselves, I, the color we want to draw. In this case, we'll draw them as red, and then the thickness of the line. We'll say thickness is 10. All right, so let's try displaying it and see how we did with the methods we know so far. So if we display the coins, you notice that the contours it found was just one giant contour. It wasn't actually able to end up closing this gap. Something we could try, given the image processings that we already know, is try to erode away from this image further. However, if you try doing that, you'll end up distorting the actual width or radius of these pennies, and then that would also distort your actual results. So unfortunately, right now, we don't have a nice way to segment this image or find the contours of these 6 separate pennies. We're going to need to use a more advanced algorithm like the Watershed Algorithm, and that has various steps to it. So in the next lecture, we're going to try the same problem here, try to actually grab these contours and see how we can do it with the Watershed Algorithm and see if it performs better. All right, so we'll see you at the next lecture where we actually do the Watershed Algorithm in order to find the foreground markers here for the 6 separate coins. We'll see you at the next lecture. Back. In the previous lecture, we were trying to find the segments of this image. However, given the image processing techniques that we already know, we were unsuccessful in doing so because we can clearly see here that there's 6 separate pennies, but the finding contour methods we know so far, even when applied with blurring and thresholding, it can only find the external contour of this general shape. Now let's try using the Watershed Algorithm to actually find the 6 distinct pennies in the foreground versus the general background. And there's a couple of steps to actually doing this, and I would encourage you to check out the notebook where we actually clearly label each step. So step 1 is to read in the image. We're going to pretend like we haven't done any of the analysis above. So starting fresh, we will read in the image, and it's in the data folder. It's called pennies. And next we're going to apply blur. So we'll say image is equal to CV2 median blur. And for the Watershed Algorithm, if you have a really large image like this, I recommend applying a really strong blur to it. So I'm actually going to choose a huge kernel size, 35. When I was experimenting with this particular image, I noticed that is what worked well for me. I would not actually recommend 35 as a default. It's just that this is a huge image. It's 4,000 by 3,000. And even with such a large image with these level of details here, I want to really blur it. Essentially, I just want 6 circles. So we're going to blur it quite a bit. And let me just show you the effects of that by displaying that image. So here we can see the 6. So there's still minor details of the face here, but clearly very blurred. Next is to convert that to grayscale. I will say gray is equal to CV2, CVT color, image, CV2, and then we'll say color. And right now we're going from blue, green, red to gray. The next step is to actually apply a threshold on the grayscale image. I'm first going to attempt to apply the same threshold we did last time. So last time I said CV2 threshold, and I passed in the grayscale, and I chose my halfway point as 127 and said 255, and then applied the binary threshold inverse. So threshold binary inverse. If I actually just tried this by itself, for this particular image, since it's been blurred so much, and often you do have to blur images quite a bit with the Watershed Algorithm, you'll notice what happens. If I say display threshold, then I end up getting some noise due to the features, which is kind of crazy given just how much this image is blurred. It's still able to actually pick up on some of those features. We don't want that. We want to try to make that just distinct circles. So what I'm going to do is apply Otsu's method. And if you can check out the Wikipedia article that's linked to this lecture, or just Google search Otsu's method, it's another method of thresholding. and it works really well in conjunction with Watershed Algorithm. You can see here the results here from the original image to the thresholded image here. So we'll come back here, and for this particular way of thresholding, you give the lower and upper limits just as the min and the max, 0 and 255, and then we're going to add in CV2, and then call thresh underscore otsu. Whoops, I did underscore otsu. There we go. So now run that, and you should get a nicer thresholded image. So there we go. We have these 6 circles. Notice they're still actually connected. So even with this more advanced thresholding technique, we can still not actually separate these without any sort of erosion taking place. We're going to also do noise removal. Technically, this is an optional step, and it won't really make a difference for such a simple image as 6 pennies, but I do want to include it because it's more or less a common step when you're dealing with more complex images. So we're going to label this noise removal. Consider it optional right now for this particular problem because it doesn't have an effect, but we will see it later on when we apply Watershed Algorithm later. So for noise removal, we're going to use the morphological operators that we're already familiar with from the image processing lectures. We'll say NP1s is a 3 by 3, and it's an integer, so we'll say uint8. So we create our kernel right here. It's just 3 by 3 of 1s, and we're going to do a bit of opening here by saying CV2 morphology, pass in the thresholded image, and then say CV2 morph open. And as we learned during the morphological operators lecture, this is a pretty good way to reduce some noise. We'll say kernel, and we'll just have it go through 2 iterations. And you can review the morphological operators lecture in case you're a little fuzzy on what this line is doing. Now, as I mentioned, for this particular problem, it's not going to really have any effect. So let's go ahead and display it. So there's the result of opening. Essentially looks almost the same, but it is an important step to do noise removal if you do have noise. And if you're trying to do a normal threshold, such as a threshold binary, removing noise would have been a good idea. It probably would have gotten rid of that noise from the faces. So we can either use a more complex version of thresholding, or you can remove noise. Kind of up to you which way to go. All right, now we're still facing a fundamental problem here. Recall what makes this task so hard is that the coins themselves are touching each other in the image. So even through blurring and dilation, morphological operators, attempts at erosion, noise removal, all that stuff, we're still dealt with this issue that we have this blob and all these points are still connected to each other. What we need to do for the Watershed algorithm is set seeds that we are sure are in the foreground. And particularly, we want 6 of those seeds. We'd want 1 seed for each center of each of these coins. So how do we actually grab things that we are sure is the foreground versus things that we are sure are the background? Well, something we can do is called a distance transform. You can check out the Wikipedia page on distance transform, but the idea is actually pretty simple. If you're given a binary image, then you should have just 0s and 1s, or 0s and 255s. And what the distance transformation does is, as pixels are further away from 0s, then their value actually ends up getting higher, meaning they'll look brighter. So you can see here, if we zoom in on the binary image, right now we just have 0s and 1s. After you apply the distance transformation, points that are further away from the 0, in this case the background, they actually become brighter. So then these get 2, and then the very center gets 3. So if you were to actually perform these distance transforms and see the results of images, you can just do a Google image search, and you'll get things that look like this. For instance, here we have a horse, and notice that only around the center is it brightest, and as you get further and further to the edge, it becomes darker. We can apply a distance transform to our threshold right now, so we can apply a distance transform to this, and we would expect only the very centers of these circles to be bright, and then slowly fade away into a dark gray as you go further and further away from the center. Then once we have that image, we can re-threshold again and then get the 6 foreground points that we're sure of. And I would encourage you to check out the resource link here on this distance transform of morphological operators, which again shows the actual operation that is occurring. As you get further away from these 0s, the value gets higher and the brightness. And what's really nice about this is if you zoom in here, you'll notice it shows you the binary images and what they become after you do a distance transform. So essentially the center of the images become brighter and things closer to black end up being faded away. All right, so let's actually check this out. We're going to perform the distance transform on this object. And the way we do that is the following way. We're going to say dist transform is equal to cv2, and then we're going to call distance transform. We're going to pass in the opening from before, and then some default values, cv2 dist underscore L2. That's just a method that actually calculates the distance. And then 5 is another default value there for the actual, if you take a look, it's the mask size. So that has to do with the way the distance is calculated. But these are good default values to play around with. All right. So again, the reason we're passing opening here is because, remember, we have opening from up here on this morphological opening. So we got rid of some noise with that step. A lot of this doesn't really look clear based on the image we're using, but they are important steps to take, and they're all labeled out for you in the actual notebook. So we're going to perform that distance transform, and then what we're going to do is say RET, and then say sure foreground. And in fact, let's actually display this image transform, or this distance transformation. Distance transform. So the result of this distance transform is the following. Notice how bright it is at the very center, so further away from the 0 values, it gets brighter, and then it turns grayer as it gets towards the outside. And now I have 6 very clear points that I'm pretty sure is the foreground. So I'll apply another thresholding to this to hopefully just grab those 6 dots. And then I will be able to apply those to the watershed algorithm, and it will understand that those are the 6 segments it should be looking into. So right now I have my distance transform, and I'm going to create 6 objects that I'm sure happen to be in the foreground. We'll say RET, sure FG, so sure foreground, is equal to CV2. I'll call threshold, and then I'm passing in the distance transform, the image above, and then I will pass in, for my limit, typically what people do is they say 70% of the max value in the distance transform. So 70% of the max value in the distance transform. And then we'll pass in 255 for the max and then 0 there. So we run this, and if we actually display now the sure foreground, we get 6 points. So all we did was threshold this image, and it makes sense that when you threshold it, you'll just get these kind of 6 smaller dots. So these 6 points, we are absolutely sure happen to be in the foreground because we did a distance transform and then we did a thresholding. And we safely did our distance transform because we had also calculated things that we were sure were in the background through this dilation process. All right, so now that we have the sure background and the sure foreground, there's kind of this in-between section. So anything that was left here that's in white that isn't present in this image in white, that's the unknown region. That's what we need the watershed algorithm to figure out. So let's actually display and find the unknown region. So we will say the following. We will say that the sure foreground, and we're going to cast it as an integer. We'll say uint 8 of sure foreground. And the unknown region is equal to cv2 subtract, and I'm going to subtract the sure background from the sure foreground. So remember, sure background, that's where I was sure I had background, and the sure foreground are these 6 points, which I'm absolutely 100% confident are in the foreground. Well, as confident as anyone can be given the algorithms, which makes sense. 6 dots here is pretty obvious. So now I have this unknown region. So let's display the unknown. And make sure I spell that right. Display the unknown. There we go. So these are the regions where I'm actually not sure if it belongs to the foreground or the background. What I'm going to need to do is make label markers out of these 6 foreground points and then have those be the seeds that the watershed algorithm uses to actually find its segments. So we'll come back down here. I have this unknown region, and then I have my sure foreground and my sure background. So now it's time for the final steps, creating the label markers for the watershed algorithm. So there's 3 steps here to actually creating these markers. The first one is actually getting the markers themselves. And we'll say ret markers is equal to cv2. And we're going to use a function called connected components. And connected components, what it's going to do is it's just going to take in our case, the image. So we're going to pass in our sure foreground image. Remember, the sure foreground image is this image right here with 6 points. So these are 6 points that we actually want to feed in as the markers. So we're going to run this. And right now, if you check out the markers, these are actually contain zeros, and we want to add 1 to all these labels so that the sure background is not 0, but 1. So we're going to say markers is equal to markers plus 1. And the reason we're doing that is because now I'm going to mark the region of unknown with 0. So I will say markers where unknown is equal to 255. Because remember, this is the unknown right here. These little donuts, that's where we're not sure if that belongs to the background or to the foreground of the coin itself. So what I will do is I'm going to label those as completely black. So we'll set that as equal to 0. And that's why I added 1 here, because I didn't want these markers to get confused with the black background of this unknown region. So let's actually display what markers looks like now. So your markers should then look like this. And essentially, this is what you have to build up to in order to build up the watershed algorithm. In the next lecture, we'll actually show you kind of a cool toolkit that does this manually. You just end up clicking and you select these sort of points. But this is the general process that's happening behind the scenes. We now have clearly labeled the background that we're sure of. So this gray in the back, that's the background that we're sure of. This black area, that's the unknown region. I'm not sure if this is foreground or background. Now in this case, it's actually pretty easy to tell that it's pretty much all foreground, but the way the computer vision algorithms work, they were unsure of this region as well. They were unsure if this was 6 or 1. But what's nice is we also labeled sure foreground, and we did it with the distance transform, which allowed us to actually set these 6 markers here. So now I have these markers that are going to act as seeds for the watershed algorithm. So then the final step is to apply the watershed algorithm to the markers. So we'll say markers is equal to CV2, and then we call watershed, pass in the original image, and then pass in the markers. Run that, and then you can go ahead and display the markers. And you'll notice that it was able to find 6 distinct markers here. And you can actually play around with the color mapping if this isn't clear enough for you, but these are 6 distinct shades of gray. Then what we can do is find the contours on the actual markers. So I'm just going to copy and paste the contours code that we used earlier. So we'll come all the way back up here. Remember, we previously used this code to find contours. So I will copy this, come all the way back down, paste it in, and I'll do one more because we still have those 3 lines of code. We'll also do this one right here. And then we're going to come all the way back down and do that as well. Except we're not finding contours on this. Instead, we're finding contours on the markers that we just created up here. So we have these markers now. Now we're going to find contours for them. And if we run this and then display the result on separated coins, notice now we were successfully able to distinctly segment each of the coins themselves. All right, so that's the power of the watershed algorithm. We did a lot of the heavy lifting on the back end. We essentially coded it all out manually. In the next lecture, we're going to set up a way that we can just click on an image, set the seeds, and then have watershed algorithm automatically fill it in for us. That's a way more convenient way of working with the watershed algorithm, but it is important that you understand the basic steps here. Let me just do a quick review of everything we did for the watershed algorithm in order to really make sure you have a clear understanding. So we started all the way back up here when we read in the image itself. So step 1 was to read in the image. Step 2 was to apply a blurring. And keep in mind, we applied a pretty strong blur because this was quite a large detailed image. So then we ended up with this. Then the next step was to put it to grayscale and then apply thresholding to it. And we specifically applied 2 types of thresholding, a binary inverse along with this Otsu thresholding that you can check out Otsu's method on Wikipedia, which works really well for large images like the one we're working with here. So then when we display that actual thresholded image, we get something that looks like this. Keep in mind, this hasn't really solved our problems because all these coins, since they're next to each other, we still have that issue that the thresholded image still looks like these are all connected to each other. So how do we actually take care of this? Well, one thing we try to do is remove noise and maybe try erosion. In this case, we didn't really have any effect, but it's a good idea to do so. And what we're going to do instead is two things. We're going to grab what we're sure that the background is, and then we're going to grab what we're sure that the foreground is. So the foreground right here. The way we grab the sure background is through dilation, which makes sense. You would just expand the foreground until you hit some sort of limit, such as iterations is equal to 3, and then you have what you're sure is left is the background. And then you're going to provide a distance transform to actually calculate the centers of your foreground objects, the brightest parts, and then you can provide a threshold on that, and then you have the things that you're sure of the foreground. Then you're going to subtract the two from each other, the sure background versus the sure foreground, and you're left with your unknown region. Your unknown region is what your watershed algorithm is going to help you solve. So using these connected components, we're going to actually grab some markers until we end up with an image like this, where we have the background we're sure of, the unknown region, and then these 6 marker points right here. Notice that they're all actually a different color of gray. Then we can find contours on those markers after we apply the watershed algorithm to it. We get these 6 distinct points on segments. We find those contours, and there we go. We were able to successfully segment this into the 6 pennies. You should also notice that it's segmented all around the image, just the general background itself. It got cut off on the top and left due to the edge, but it did that as well. Okay, definitely check out the resource links. If this all was a little too complicated for you, don't worry about it too much, because the very next lecture, we're going to show a simplified version of using the watershed algorithm, which is a lot more interactive. We'll see you there.